Hi everyone, my name is Chelsea Finn. I'm an assistant professor at Stanford, and today I'm going to be talking about meta-learning symmetries and distributions. So to start off and provide some high-level motivation and also an introduction to myself, I'm interested in, and my students are interested in, how we can develop broadly intelligent behavior through learning and interaction. And a lot of the work that we do involves actually doing experiments with robots in the real world. Robots that can learn how to use a spatula to lift an object and place it into a bowl. Robots that can learn to place blocks into shape sorting cubes through trial and error. And also robots that can watch a video of a human doing something and use that to figure out how to place an object into a certain container. The reason why we're interested in studying robots is that I think that robots can teach us things about intelligence. And in particular, if we hope to build general purpose robots that can operate in real world environments, they must be able to generalize across tasks, across objects, across terrains, across environments, and so forth. So it's a really rich and interesting test bed for studying challenging learning problems and challenging problems regarding AI. Now, in this talk, I'll be providing a perspective on generalization, and a lot of things, while at a high level, come from some of the challenges that arise in building embodied intelligence in the real world. Many of the things I'll be talking today are not specific to robotics and are general to many challenges in machine learning. When thinking about generalization, I think we often are faced with problems like this, where our train distribution is much narrower than the kinds of situations we want to be able to generalize to at test time. For example, maybe our train distribution is a robot trained in the lab, and our desired test distribution is the real world, where there are many different kinds of objects and many different kinds of environments that you may encounter. Or in computer vision, maybe the train distribution is ImageNet, and then again, the test distribution, the desired test distribution is the real world, where we again see in a broader distribution, you tend to perform more poorly. So how do we go about extrapolating beyond the training distribution? Of course, if we're training with a standard IID machine learning setting and not making any additional assumptions, then we won't be able to extrapolate. And one very natural approach to think about how we might extrapolate is to build in some sort of structure into the learning process and some additional assumptions into the learning process that allows us to generalize further. And the structure may be compositional structure or symmetries such as equivariances. Then the key question is, how do you actually build in this structure? And how do you determine what structure to build in the first place? One natural thought is, well, I know how to generalize pretty well. How would I build in structure by hand? But I think that we're actually really bad at building in structure into our models. Just like we're really bad at building feature detectors. And we saw it in the past, in the history of computer vision, feature detectors and features that were learned performed significantly better than features that were constructed by a human. And this is what led to a tremendous amount of progress on ImageNet classification, for example. So while we're bad at building feature detectors, we're really good at learning from data. So what I'd like to talk about today is, can we learn structure from data and then transfer that structure to new tasks? Hopefully in the end, such that we can generalize and extrapolate to things that we haven't seen before and things that are potentially outside of our training distribution or drawn from a distribution that's shifted. And to do so, we're going to build upon ideas in meta-learning. So first I'll give a very brief primer on what meta-learning looks like, and then talk about how we can actually leverage meta-learning to try to solve this question. So how does meta-learning work? Let's start with a simple example of how the training setup looks like. One common use case of meta-learning is the problem of few-shot image classification, where we're given one example, in this case of 5 different classes, and using these 5 data points, this very tiny training data set, we want to be able to generalize to new examples and classify them as being among one of those 5 classes. This is essentially our test set. Now, of course, if you train from scratch, you wouldn't be able to perform very well on this few-shot classification problem. But what you can do is if you can leverage previous data and learn structure from previous data, that will allow you to generalize to this few-shot classification problem. So what we can do is construct data from other image classes in a way that prepares us for this problem here. For example, we can construct data from image classes like this, and so forth, and essentially train a model or an algorithm such that after it sees each of the training data sets on the left, it can effectively generalize to the test data on the right. We'll essentially learn how to learn these tasks for a range of training classes such that when we're given a few examples at meta test time of some new image classes, we can effectively learn and generalize from a small amount of data. So this is the gist of how meta-learning works. You meta-train across a number of different tasks. These tasks could be image classification problems, but they could also be a range of other problems, such as reinforcement learning problems or regression problems. And after this, you try to be able to generalize to new tasks. So this is what the training setup looks like. And one approach for doing this is to embed an optimization process inside the learned learning process and train that overall learning process in a way that generalizes with a small amount of data. So for example, we might have some set of initial parameters. We then take our tiny training data set that's labeled with corresponding labels. We run gradient descent starting from the initial parameters to get a new network. We then pass one of our test images into this new network and train it to predict the correct label. Now, notice that we can actually backpropagate end-to-end through this learning process into the initial parameters and other hyperparameters such that fine-tuning and such that this optimization works well with a small amount of data. That's the key idea behind optimization-based meta-learning algorithms, including the model-agnostic meta-learning algorithm that learns initial features that are suitable for fine-tuning with small amounts of data. So this is one approach, and this is the approach that we'll be leveraging in the first part of this talk, and we'll also leverage another kind of meta-learning approach later. So while meta-learning allows you to learn some structure from tasks such that you can try to generalize to a new task with a small amount of data, it doesn't completely allow you to solve the distribution mismatch problem. Essentially, what meta-learning gives you is it allows you to lift the problem up to a higher level from trying to generalize from data points to then trying to generalize to tasks. But we still need to assume that the meta-training task distribution and the meta-testing task distribution are the same. And if we're in a situation like this, where the task distribution is different at meta-training and meta-testing, then we're still out of luck. So oftentimes we're in the situation where we want to be able to learn new tasks that are related to the meta-training task distribution, but not necessarily draw an IID from that meta-training distribution. Where by related, I mean tasks that share some certain structure. And today we'll be talking a bit about how we might try to explicitly extract that structure in a way that allows us to generalize more broadly. So first, we're going to try to answer the question, can we discover equivariant and invariant structure using meta-learning? Can we discover symmetries in the data with meta-learning? And second, we'll talk about, can we adapt a distribution shift using the structure recovered by meta-learning? Okay, of course, there are a number of different types of structure, and so we'll first start by focusing on equivariant and invariant structure, but it's possible that the ideas that we'll talk about will allow us in future work to extend to other kinds of structures as well. But first, let's think about equivariant and invariant structure. Now, the first question is, does MAML already do this? Does it already extract this kind of structure? Well, MAML can learn equivariant initial features or invariant initial features, such that the initial parameters exhibit certain kinds of equivariance, but the equivariance may not actually be preserved in the gradient update. So the updated network may no longer preserve some of those properties that we would like. So essentially, MAML can't extract this sort of structure in a way that is preserved both in the initial parameters and in the latter parameters. So our goal in this work is we want to be able to figure out if we can decompose the initial weights into equivariant structure and the corresponding weights irrespective of that structure. And if we can do this effectively, then in the inner loop, we can update only the weights and retain the equivariant structure such that we have a neural network that's equivariant to certain transformations, both in the pre-update as well as in the post-update network. So what exactly do I mean by this, and how might we actually do this? So let's actually look at examples of how equivariances are represented in neural networks. So we can start with a very common example that we're all should be very familiar with, which is convolution. And a 1D convolution layer looks something like this, where you have some filter weights that are denoted with W, and those are slid across the image such that the resulting output is translation equivariant. So this is an example of a layer. How might we actually try to go about kind of parameterizing this layer and parameterizing both the filter weights as well as the kind of transformation, the kind of structure that is represented? Well, to do so, what we'll first look at is how we might represent a 1D convolution using a fully connected network. So the way that looks is the following, is what's shown on the right. Essentially, again, X and Y are the same as on the left, but now we're going to be representing our weights instead of as this convolution filter as a fully connected weight matrix. And what we see is we get this matrix right here where ABC is copied multiple times in the weight matrix and the rest of the weight matrix is 0. So we have both this sparsity pattern as well as this weight sharing pattern. Now what we're going to try to do is we're going to try to figure out how we might essentially decouple the filter weights and the structure. And so what we're going to do is we're going to take these ABCs, these are kind of the underlying weights. We're going to try to take those and also take the equivariant structure, such as the structure of convolutions, and decouple those two things and then construct a weight matrix from that decoupled weights and structure. And in particular, what we'll try to do is we're going to reparameterize the weight matrix of a neural network as follows. So we're going to have a set of parameters. For example, this would be A, B, and C in the previous example. And we'll take these vector parameters and multiply it by what we'll call this sharing matrix. Now, the result of this matrix vector multiplication will be another vector. And we'll take that vector of weights and reshape that into the weights of a fully connected neural network. Now in this example, we can see that the resulting layer weights here correspond to a permutation equivariant function, such that if you permute essentially either of the two inputs X that these weights are multiplied with, you'll also get a permuted output. So this is kind of another example of an equivariance that you can represent for this particular sharing matrix. And it turns out that we can show that for different sharing matrices, you'll get different kinds of equivariant structures, such as permutation, rotation, translation, and so forth. We can actually theoretically prove that this decomposition of a sharing matrix and these underlying parameters directly corresponds to a decoupled equivariant sharing pattern and filter weights. And the way that we prove this is using some formalisms in group convolutions, group convolutions are essentially a generalization of the kind of convolutions that we use in convolutional neural networks that can generalize convolutions not only to translational equivariance, but many other forms of group equivariances as well. Essentially, group equivariances for any closed finite group. Okay, so now that we have this reparameterization of our weight matrix that's decoupling the equivariant structure and the filter weights, what we can do is we can meta learn the equivariance and keep the equivariance fixed in the inner loop while only adapting the weights. So in particular, the inner loop of our meta learning algorithm is only going to update the weights V and keep the equivariant structure U fixed. So what this looks like is our weight matrix is reparameterized as U times V. The inner loop gradients shown in red are going to be back propagated through U into V. and only V will be updated as shown in blue using this inner update. And the equivariant structure will be fixed both before the update and after the update. And so this allows us to ensure that equivariant structure is preserved within the inner loop of the algorithm. And then in the outer loop, we will learn both the equivariance U and the initial weights V such that we perform effective few-shot generalization. So this essentially gives us a way to learn equivariant structure, such as the structure represented by convolutions and other transformations. So we refer to this approach as meta-learning symmetries by reparameterization, or MSR. So in our experiments, we wanted to test a few different questions. The first question we wanted to answer is, can we discover convolutions from translationally equivariant data? And to study this question, we constructed some synthetic data that was translation equivariant along one dimension. So the data corresponded to a vector of inputs and a vector of outputs, and the data was constructed using various translation equivariant functions. We did this for many different functions, and meta-learned both U and V from this multitask data. And what we see is if we compare MSR starting with a fully connected architecture, if we compare this to MAML with fully connected layers, locally connected layers, and convolutions, we see that MSR, starting with a fully connected layer, is able to achieve performance that is comparable to the performance of MAML with convolution layers, indicating that it's able to learn something to effectively process this translation equivariant data. It's also able to significantly outperform MAML with fully connected layers and MAML with locally connected layers. Now, what's really cool about this is we can actually visualize the weight matrix and kind of the reparameterization that it learns. And we see that it exactly corresponds to the matrix that I showed earlier. It exactly corresponds to convolutions. So essentially, we find that MSR is able to discover convolutions, at least in this very simple example, from synthetically generated translationally equivariant data. Now, the second question we wanted to answer is, can we discover something that's better than convolutions in certain situations? So for example, maybe we have data with partial translation symmetry. In this case, the way that we generated this is we took a locally connected function and assumed that the locally connected function had low rank, such that there is either one filter that is used for the locally connected layer that would correspond exactly to convolution, or if there was two filters that were used, or if there was three filters that were used, essentially having rank 1, 2, or 3. And what we find is that for each of these, in this case, 1, 2, or 5, in this case, we find that MSR, starting with the fully connected layer, is able to effectively discover this partial translation symmetry in all of these 3 cases. And MAML with convolutions is able to do well in the k=1 case, as shown before, but as you increase the rank of this locally connected function, it isn't able to perform well because it's making too restrictive of an assumption on the filter weights. And then we also find that MAML with locally connected layers and fully connected layers also isn't able to perform well because it isn't able to recover this equivariant structure and keep it fixed within the inner loop. So here's one example. Another example is, well, what if we have data that's translationally equivariant, but also rotationally equivariant and has reflection symmetry? In this case, we find that MSR is able to find and discover a structure that is stronger than translational equivariance and perform well both with data that is translationally and rotationally equivariant, as well as data that is translationally equivariant, rotationally equivariant, and reflection invariant. Sorry, reflection equivariant. So, and it's able to strongly outperform MAML with convolutions. And note that in this experiment, we actually started with convolutions and applied MSR on top of convolutions to learn the additional equivariances. Okay, now the last question we'll want to answer in this work is, can we learn symmetries from augmented data? In this case, we're going to actually use real data and not any synthetic data. And we're going to see if we can essentially bake in the augmentations that data augmentation gives you into the architecture and into the learning process itself. To do this, we'll follow this simple algorithm here, where we have some meta-training tasks, we have a meta-learner, as well as a data augmenter. And then at each iteration, we sample a batch of tasks. That batch of tasks is split into a train set and a validation set. We then augment only the validation set and then apply the meta-learner such that it can be adapted on unaugmented data and do well on augmented data. Essentially such that it can learn effectively from data that's not augmented and perform well on a much broader set of data that is augmented. Essentially, we want to bake the data augmentation into the architecture, into the update rule, such that it can effectively generalize to augmented data from only unaugmented data. So to do this, we used the Omniglot dataset and the mini ImageNet dataset. And the augmentations that we used included a range of standard data augmentations that are used in computer vision, including random crops, which kind of denote translational invariance, some small rotations, and other things like lighting and reflection and so forth. And what we find is if we first compare MSR to mammal, we find that we're able to do significantly better by learning both the by decomposing the equivariant structure and the weights and adapting only the weights in the inner loop. We're also able to do better than almost no inner loop, which essentially only adapts the last layer of the network. And this tests that whether, basically, in principle, something like almost no inner loop or ANL should be able to do well when you have equivariant features and you just want to learn a function on top of those equivariant features. But we find that we're able to do significantly better than that by actually representing this equivariant structure explicitly. And we also find that we're able to outperform prototypical networks in the most complicated setting in mini ImageNet, while prototypical networks performs about comparably in the Omniglot setting. Okay, so to kind of summarize, I think that this reparameterization of equivariant structure and weights provides a framework for understanding the interplay of features and structure in meta-learning. It allows us to decompose which is having an effect on, whether features and structure are having an effect on the fast adaptation process. And I hope that it may also provide a number of interesting directions for future work that allow us to actually try to extract structures from different natural data sources and use that structure to understand the data or to better learn other tasks. So far we've showed how we could learn symmetries. And the goal of using this sort of structure, compositionality, symmetry, and so forth, is usually to get better generalization. And we showed that we were able to get better generalization to, for example, to augmented data. But now I'd like to talk about how we might get better generalization in the setting where you have distribution shift. Essentially, can we adapt a distribution shift using the structure recovered by meta-learning? Okay, so first we need to characterize the kinds of distribution shift that we're going to be expecting. And in this part of the talk, we'll be considering what's called group shift. So there have been a number of works that study this sort of distribution shift. And what this looks like is you assume that you have a categorical group variable Z. And this variable Z could represent gender, race, some background scene, a variety of different concepts. And we assume that these group variables are going to be known during training. Essentially, for each data point, we'll know both the input, the label, as well as the group variable Z. And then the kind of shift that we'll expect is we'll assume that our training data is drawn from this distribution and that our test data is drawn from this distribution, where P of X and Y given Z is going to be the same at training time and test time, but P of Z may change in various ways. And it may change really in any way possible. And this can capture label shift, and can capture most forms of covariate shift as well. Okay, so one kind of popular approach for trying to be able to be robust to this kind of shift and be able to handle this kind of shift in your distribution is what's called distributionally robust optimization. And the key idea behind this approach is to form an adversarial distribution Q of Z and train your model to be robust to this worst case distribution Q. So essentially what this equation is showing is that we're going to be minimizing our training loss L for our network G under the worst case distribution Q of Z. So essentially the adversary gets to pick Q, P of X and Y given Z is given by the data, and then you're minimizing your loss with respect to that adversary. The benefits of this approach is that it can enable robust solutions amidst group shift, and is also less pessimistic than adversarial robustness because you're constraining the shift to be with respect to this categorical group variable rather than considering a wider range of shifts, such as changing pixels, for example. But the downside of this approach is that it often sacrifices average and empirical group performance. It often is still somewhat pessimistic with respect to the group that you may see at test time. What we'd like to do instead is aim to adapt to distribution shift instead of aiming for robustness, so that we can try to adapt to different distributions given a small amount of information from that distribution. And in particular, we're going to assume that at test time, we're given some test inputs available in a batch, and that batch of test inputs will be from one part of our distribution. And our goal will be, given those images that are representative of that group, can we then adapt to those images, adapt to those unlabeled images, and be able to essentially adapt to that distribution shift, to that part of the distribution, so that we can perform better. So we refer to this as adaptive risk minimization in the sense that you're being adaptive at test time rather than minimizing risk for the empirical distribution. And the idea behind our approach will be to first construct sub-distributions of the training data. This will use the group data, the group information, and then we'll train for adaptation to different sub-distributions. And we'll train for this adaptation in a way that the adaptation is performed with only unlabeled data. So the way that this will work is at training time, we'll assume that we have a data set of inputs, labels, and the corresponding groups. We'll then sample a sub-distribution using these groups. I'll go into some of the details of that a bit later. Sample a sub-distribution and learn how to adapt from that sub-distribution, constructing a classifier that takes as input essentially the context of the sub-distribution as well as the label. And we'll construct the sub-distributions using group information. So we may kind of consider a uniform distribution of all subgroups, of all potential subgroups, and we'll also consider potentially other more specialized things based on the particular application. So how does this actually work at a kind of more mechanistic low-level point of view? What we do is we have, instead of using a gradient-based meta-learner, we're going to use what's called a contextual meta-learner here. And the reason why we want to do this is that the data that we're adapting to is completely unlabeled, so it's a bit difficult to figure out how you'd adapt with gradient descent to unlabeled data. So in particular, we'll consider the unlabeled images from our sub-distribution. We'll then pass that into a neural network that computes a contextual embedding of that sub-distribution. And then we'll take our query image that's also from that sub-distribution, pass that into another neural network to make a prediction y hat 1. That prediction will be compared to the label that will give us a classification loss for that query image. We'll then backpropagate this classification loss into both the neural network that takes as input the query image, as well as the neural network that takes as input the context, the unlabeled data, and train it such that it can effectively adapt to both the unlabeled images as well as, and for a variety of query images. And we'll do this for a variety of sub-distributions that are sampled according to group data. Okay, so in our experiments, we compared adaptive risk minimization to both kind of standard empirical risk minimization, as well as to distributional robustness, and in particular, this paper by Asagawa, Ko et al. That actually combined and showed how you could use distributional robustness with neural network training, which is actually a bit non-trivial. And also to a baseline that essentially does ERM, but it upweights the groups to the uniform distribution over groups. And we'll refer to this as UW in the sense that it's upweighting groups according to the uniform distribution. Okay, so our first experiment is going to be on a really simple situation where we're going to be considering the MS data set, and group shift will be caused by rotations in the image. And our data distribution is going to be significantly skewed towards some distribution, towards some image rotations, and some other image rotations will be significantly underrepresented in the training data set. Now, what we see is if we plot the accuracy as a function of the rotation, we find that ERM, distributionally robust neural networks, as well as an upweighting baseline, do significantly worse on the underrepresented rotations that are around 50 degrees, while adaptive risk minimization is able to leverage the data, the unlabeled data that it gets at test time in order to adapt to the rotation and get a significantly higher accuracy. Quantitatively, if we look at both the worst case accuracy for the worst image rotation, as well as the average accuracy, we also see that ARM, with these numbers, is able to significantly outperform prior approaches on both of these metrics. Okay. On our second experiment, we look at the SLEB-A dataset, and in this case, the task is to predict the is blonde binary attribute, and the group shift will correspond to both gender and hair color proportions. In this, in the original dataset in SLEB-A, there's actually a spurious correlation between gender and hair color, and so we want to be able to study situations where at test time that spurious correlation may be different, and the proportion of gender and the proportion of hair color may be different than what you saw during training. What we see in this case is, again, that by adapting to kind of some data from a particular distribution, ARM is able to do significantly better, in this case on worst case accuracy, as well as average case accuracy. In this case, ERM is able to do the best on empirical accuracy, but ARM is the second best in this category. And unlike DRNN, doesn't sacrifice empirical accuracy quite as much as the other cases, quite as much as DRNN. Okay, and then lastly, we looked at a federated learning setting. And in this problem, it's a data set that is somewhat inspired by MNIST, except instead of only having digits, there are also all the letters in the alphabet, in the English alphabet. And the group shift in this case is going to correspond to different users and how different users write different characters. Essentially, we want to be able to adapt to a different writing style of a different user. And we want to be able to adapt with unlabeled data. So in many federated learning settings, you actually assume that you have labeled data for each new user that you might be given. This is actually somewhat impractical because it requires each user to label data for the machine learning algorithm in order to allow it to adapt. And unlike what most kind of group robustness settings consider, we're actually going to be adapting to entirely new groups at test time. And what we see is, again, we compare to ERM, an upweighting baseline, and a federated learning method, as well as kind of a simple sanity check that ablates whether the context is actually useful for our method. And we find that we're able to significantly outperform on all three: worst case, average, and empirical accuracy, and actually do quite well across the board. And to give a sense for what the algorithm is actually doing, we can look at a qualitative example. So here's an example of an image in the data set. And this image is actually a bit ambiguous whether it's a 2 or a lowercase a. And in the data set, there's actually more, 2s are actually, in general, have a higher proportion. There are many examples, there's many more examples of digits than there are of characters. So ERM actually incorrectly classifies this as a 2, whereas if you use context from this particular user, you can see that there are examples of different characters that it wrote, that the person wrote, and this looks kind of, you can look at essentially how they write a 2, how they write an A, and even though these images are unlabeled, our adaptive risk minimization method, which uses a contextual metalearner or CML, is able to accurately classify this as an A, using 50 unlabeled examples from that user, while ERM incorrectly classifies it as a 2, And ARM, when only given the two images shown in the black dashed box, it also incorrectly classifies it as a 2 because it doesn't have enough information about the distribution that this has to be able to handle at test time. Okay, so to wrap up, today I talked about how we can try to discover equivariant and invariant structure via meta-learning, essentially discover symmetries in the data and transfer that to new tasks. And I also talked about how we can adapt distribution shift using structure recovered by meta-learning, and specifically looking at distribution to various groups. I'd like to thank my students who played a large role in the work that I presented today. If you're interested in learning more about generalization, multitask learning, and meta-learning, I'd encourage you to take a look at my course. All the lecture videos are available online and hopefully will be a good resource to people interested in learning more. And thank you for your attention.